Hello everyone, I welcome you all in this lecture. So altitude hold loop part was completed. Now we will study the heading hold loop. Okay. So basically I have drawn the same diagram which I have talked to you regarding altitude hold. I will try to connect this loop to the altitude hold loop so that you will remember easily and you will try to connect the concept more easily. So like in a pitch we have delta ES elevator. One by one we will do, no, not a problem. So here I can write heading hold loop. Okay. So now we are going to change this loop for a heading hold loop. So I already explained to you about the pitch loop. I mean to say, by deflecting the elevator you will generate the pitch rate, then pitch angle, and finally at a one particular pitch angle you can actually hold the altitude. That is how we have done. Okay. Now we will try to change this loop to heading. So in a lateral case, for example, when you deflect aileron this down, this up, then there will be more lift here, less lift here. So L plus delta L, N minus delta N. This is how we will roll, and then one centripetal force L sine phi will try to rotate in a circular path. So basically here first thing you are going to deflect as a aileron. So here you replace delta E by delta A. Okay. So here I am going to replace delta E by delta A. So like a pitch rate you have a roll rate, right? So you just replace this transfer function. Already we have derived this P by delta A of S. Okay. And you will get roll rate. And when you integrate you will get phi. Okay. And here what you are going to multiply? You are going to multiply, which we don't know. We have to find out. Okay. So we can find out like this. We know that uh, tan phi, when you take a bank, L sin phi equal to mv square by r, right? And L cos phi w. So you divide both equation. Tan phi equal to, you will write v square by r into g. So if phi is small, you can consider tan phi as a phi, and then v by r take separately, and then v by g. So v by r you can write a psi dot, and then you can write psi dot equal to phi g by v. So in phi, if you have to multiply by g and divide by v, you will get the psi dot. Okay. So g divided by v. Okay. You will get psi dot, and once you have a psi dot, okay, you may integrate, like for example, by just putting the s here, you will get psi. Okay. And here what you will command? Here you will command, here you will command psi command. Okay. Okay. So this will be phi command then. Okay. This will be p command then. Okay, and this you can multiply as a kp, right? So how beautifully I have changed from altitude to the heading hold loop by replacing just delta E with aileron, Q with P, theta with phi, H with psi. Okay, psi is a heading angle. How much angle it is making from the north? Okay, let's say this is aircraft is flying in north direction. Okay, so psi is 0, flying in this direction. So what angle it is making? That is nothing but the psi. All right. So already I have explained about the all the loop. This loop is called stabilization because here you are multiplying the feedback with the gain, and remaining 2 and 3 are the tracking controller because here you are tracking phi, here you are tracking psi. Okay, inner loop will be most fast, will be run at a faster frequency than compared to the other loop. So fast, little fast and slow, like that you can differentiate. Okay, why? Because already explained to you, if some disturbance comes, for example, like a very standard example, if the quad rotor is hovering, some wind is coming from that direction, so it will try to drag the quad rotor. So you have to immediately rotate the quad rotor very fast in order to counter that wind. Otherwise, you will drift and then again come back. So that is why the inner loop should act as very fast. Okay, all right. And how we have changed from phi to psi, I have already explained to you from this. All right. If you have any question, please ask me. Okay. And one interesting thing you will see, even if you put kp equal to 0, there will not be any problem because in a roll subsidence, for example, when you try to disturb, immediately it will come back to the original position. There will not find any kind of oscillatory motion when you consider the pure rolling motion. Okay, first order transfer function. So already well damped is there. Damping is 1 already. The roots are on the real axis. So you no need to have any kind of value on a kp. Okay. Sometimes if you choose kp value, it will destabilize your system. So be careful with that. Okay. And this is a PI controller, proportional integral, that also I explained the while teaching you the altitude hold controller. Okay. So basically here what is happening, you are deflecting the aileron, maybe you can roll that this side also and that side also. Okay. If you deflect the aileron in this side down, this side up, it will take a L plus delta L this, L minus delta L this wing. So it will take roll, and using L sin phi, this L sin phi m square by r, it will take a turn. Okay. So that means how this aileron, roll rate, phi angle, psi angle, all are connected. So as a control system engineer, you should have a feel for all kind of feedback what you are going to take and how it is affecting your system and how these different feedbacks are connected to the each other. Okay. So as a pilot, as an engineer, okay, as a scientist, just you can think that how I can roll. So the question is simple: deflect the aileron down, up. If you want to rotate in this direction, then there will be rolling motion, and finally you can attain one kind of heading angle. So that is exactly happening here. You can command size some 30°, 45°, 90°, even 360° with some standard rate of trim. Like in a commercial aircraft, the heading is commanded generally 3° per second. So for example, let's say if you are taking the takeoff from Delhi, but your Bangalore is that back side, for example, in this direction, so you have to take a 180° turn. So what you can take a takeoff, no problem, but you might have experienced that sometimes please taking a turn like this 180° and then finally flying towards the Bangalore. So that is how this loop is actually running in that condition. Okay. So that is a beauty of a controller. You have to go in depth, understand each and everything, what feedback, what is doing, how the gain is selected, Okay, how the gain is playing the important rules, what kind of the disturbance and all. Ask yourself, okay, and try to put the same in the comment section. I will try to explain. So this is about the hidden hold loop. The same thing we are going to implement in the MATLAB and Simulink in the next lecture. Thank you so much.